Well, welcome to lecture 24. We'll be covering the Rayleigh Ritz method part 2. And what I plan to do today is to cover a few more examples and kind of give you a top level view of what we've accomplished so far. In this particular course, the energy methods and computational structural mechanics, which the course is named structural mechanics, but the ideas can be applied to any area of expertise that has partial differential equations. The purpose of this course is to develop and derive uh, methods that allow us to solve an approximate solution to partial differential equations. And in this particular course, we're focusing on problems that have physical solutions. They're physically based problems. And so the way we started the course, the first quarter of the course, we started with some mathematical foundations. And we covered the idea of calculus of variations, how you find that one function that minimizes a functional or maximizes a functional. You don't know that until you examine the second variation. And that showed us that to do that, we need to solve the Euler-Lagrange equation, which comes naturally from minimizing or extremizing the functional in question. And from there, what I did, I then derived a number of equations uh, using structural mechanics. And so I started with um, deriving the governing equations of elasticity. And I could have chosen a different area of expertise, like heat transfer or fluid mechanics, but I chose structural mechanics. And I then derived the equations for that using the integral form of Newton's law and came up with the 15 equations and 15 unknowns that comprise the equations of elasticity. And those are the strain deflection relationships, those are the, the stress equilibrium equations, and the stress strain constitutive law. From there, I moved on and said, okay, what if I use an idea based on calculus of variations? And consider now the principle of virtual work, where the internal virtual work equals the external virtual work. And that's the most general framework you can ever have for structural mechanics. When I applied that to a 3D problem, I found that the Euler-Lagrange equations miraculously was in fact the stress equilibrium equations with the Cauchy's relationships as the boundary condition. That was quite exciting actually. And then I went in and used principal virtual work to derive three structural theories. We derived the elastic bar problem, Euler Bernoulli beam theory, Timoshenko beam theory, and then in the problems you're solving off class, you're going to see even more advanced theories that you'll be looking at. And later on, just to remind you, I'm not done deriving structural theories. I'll be deriving the torsional theories. We're going to be deriving the Kirchhoff love equations will be for plates, and then we'll be deriving the the Reissner-Mindling plate theory, and then maybe later on we'll be even covering shell theory if we can get to it. So that's one aspect of applying calculus or variations is that when you use the principal virtual work and you make some modeling simplifications, maybe from 3D to 1D or 2D, you will expect some error there. And that's why calculus variations is so powerful because it's going to do its best to give you the best Euler-Lagrange equations possible for the given problem. Note that there will be errors in these solutions. These solutions are not perfect, but they're good enough for engineering. Just imagine if I took an aircraft fuselage skin and I went in and tried to model everything 3D. That would be computationally too expensive. But instead, if I can simplify the modeling approach to 2D, then maybe there'll be errors, sure, but it's good enough for engineering. And so that's where the power of calculus variations was shown to you. And then I applied it for very specific problems like Casigliano's theorem, which is actually also based on calculus variations. And the benefit there is they can now solve for particular deflections at particular locations. Maybe you cannot get the full field solution for the whole problem, but you can find the deflections at particular points in the system in a very simple way, just by calculating the strain energy. I then took the principal virtual work and simplified it to and found that can derive something called the theorem of total potential energy. And we found that the theorem of total potential energy is found by making two fundamental assumptions. The assumptions are: assume a conservative deformation process, which means I apply a load to the system, and then when I remove the load, I recover the elastic deformation. Sorry, I have an elastic deformation, so when I remove the loads, it goes back to the original configuration. Secondly, what we did there was to then derive. Um, Second thing, the second assumption was that the loads are conservative, meaning the loads do not depend on the deflections. So when you make those two assumptions, you arrive to the total potential energy. And what we demonstrated was that if I took the first variation of the total potential energy and set that equal to zero, in other words, I extremize a functional which depends on displacements, that when I do that, I'll get an Euler-Lagrange equation. And when you solve for the deflections to that Euler-Lagrange equation, those are the deflections that render the system in equilibrium, but those are the ones that also minimize the total potential energy, which is a functional. And so as a consequence, we were able to then talk about this idea called the minimum term of total potential energy. And so from there, then I took another step back, and kind of said, okay, why is this why all this is useful? And the idea is that, I took a step back into mathematics and covered the idea of adjoints. And the idea of adjoints is basically if you have a functional and I'm interested, or sorry, I have a governing equation that's representing a physical problem. Maybe it doesn't represent anything, it's a mathematical problem. But the idea there was if I have a governing equation, can I construct a functional? And you can construct a quadratic functional in cases where the system is conservative, where a self-adjoint, where the system is shown to be self-adjoint. And if I can construct a functional, perhaps I can use this idea uh, here called the Rayleigh Ritz method, this approximation method here. This approximation method is beautiful because what I'm going to do is to assume an approximation where now I'm basically fixing the space of functions considered. You can imagine that if I'm trying to find the function that minimizes a functional, there's infinite number of functions I can select from. And that to me is incredible that calculus of variations can actually tell you what is a function that actually does that. Because imagine, I mean, there's sinh function, cosine functions, e to the x functions, there's sine and cosines, and there's so many functions that exist, yet calculus of variations can tell you which is the one. But now, I'm not very interested in solving and finding what the exact function is that does that, because that's a lot of work, and it's not systematically possible to implement something like that in a uh, computer code. But instead, what we found was that we can go ahead and instead, um, maybe instead of solving for that exact solution you see here, I mean, this is the exact solution, by the way, to this crazy problem here of a heat transfer. Laplace equation with some boundary conditions. It's pretty insane. But, no. Let's come up with a way of turning the problem into some sort of matrix times temperatures equals some loading condition. And when I invert that, I can calculate the temperatures and plot them up. A linear system of equations instead of getting the exact solution. And so the idea then was to come up with an approximation that's basically a an approximation that depends on known coefficients times basis function you selected on purpose yourself. You selected them a priori to meet certain criteria that I had discussed. And when I plug in the approximation function into the functional now, guess what? Now my functional just becomes a regular function just from calculus, because now my functional became a function because it only depends on the unknown coefficients, which are not functions, those are just unknown scalars. And so now I can find the functions, the coefficients that minimize that functional or function now, because it's a function now. And if I'm able to do that, what I've actually done indirectly as well is to solve the Euler-Lagrange equation, a differential equation. And so that was the idea there. And so let's go and now revisit that a little bit today. Given the total potential energy here, and that's the total potential for total potential energy for a linear system. And so for a linear system, that's clearly 1/2 sigma xx epsilon xx. And I'm using, instead of in the index notation, I'm using this, which is totally fine. And of course, you can write this in vector notation, the stress vector times epsilon vector. And sigma stress is equal C times epsilon. And so when you apply the transpose here, you get, you rearrange everything. C transpose is your stiffness matrix. And the stiffness matrix here, the transpose of that is just the regular C because it's symmetric. And so that's what you will get. Um, and so, yeah, so that's what we get. And if you're trying to remember how we got to this for a linear system for 1D, if this is a stress strain curve, then the area under this curve gives you that strain energy density. And so that's clearly sigma xx, 1/2 sigma xx epsilon xx, which is the area under this triangle. And then we talked about tractions. The tractions are applied loads on the surface and the body loads. And when you do that, again, I'm not using index notation here, which is fine, but sometimes it's kind of cool not to see index notation because index notation can sometimes make it look very strange, and you may not even see the physics. Again, this is a strain energy stored by the body in terms of deflections, right? And to get a total potential energy, you have that strain energy, the total strain energy, and then you have to add to that the potential energy. So potential energy, the body forces, Bx. Remember, the body force is a vector, so dot that with the displacements, and you get Bxu plus Byv plus Bzw, where uv and w represent the translations of a particular point in the system in three directions, x, y, and z. And you may have seen this before, written more nicely in index notation, BIUI, same thing. And then here I have the tractions applied on the surface, again, TIUI, but now I'm not using index notation, but that's the way it looks like. And I can apply point forces, of course, if I wanted to. Some point forces here, why not? So then you have, for that single point force here, PXU minus PYV minus PZW. And so then the total potential energy then becomes all this strain energy minus the, or plus the potential energy, because we define the potential energy to be the negative. So there, that's what you get. And that's beautiful here. That's what we get, and that's beautiful here. Um, so 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 the idea then is to apply the principle minimum potential energy, because if I apply that, I can perhaps find the Euler-Lagrange equation. And the Euler-Lagrange equation is going to be the governing equations of elasticity for this problem, which we all know what that is. And when I solve for uv and w out of this governing equation, that uv and w is the one that renders the system in equilibrium, but also extremizes pi or minimizes pi. We know it minimizes pi because the total potential energy exists, and I already told you is of quadratic nature. And one of the problems you're going to be looking at offline, you're going to be proving that, and you're going to see that in one of the problems in the that you'll be looking at. So very cool. That's what we did, and I'll go through the formulation for this in 3D in a minute, or maybe a little bit later. But if we consider the elastic bar, and you go through a derivation of the elastic bar, which we've done several times now, so I don't want to spend too much time. But say I have a load applied here with a deflection, a load applied here with a deflection, applied load Q here. If you apply the theory of 1D elastic bar, which was covered in several lectures back, you're going to see that the potential energy is simply this. And when you go through this derivation, you just find the total potential energy as a function of deflection, which is very nice. So in 1D, I went from 3D and then simplified it to 1D elastic bar. Again, a number of assumptions made when you went from 3D to 1D, so you will expect a number of errors as a consequence, which is okay. Those are assumptions you're making, but calculus variation is going to help do the best it can with what you fed it, right? It's the way I see calculus variation is this box where you feed information, and then as an output, it gives you the best Euler Lagrange equations that extremizes the functional. And so from here, we got that, and then from here, we can now extremize pi by finding the first version of pi. I did it here very quickly. Instead of v, we've been using eta, so it's the same thing. And then you integrate by parts, and when you do all that and integrate by parts, you get the strong form or the governing equation of the problem. When I say strong form here really means the differential equation in question. I don't want to go through this derivation because you are an expert, a true expert at how to handle this. So we're not going to go through that. But minimizing pi here definitely gives you the Euler Lagrange equation shown in this here, and that's also called the strong form of the problem. So we'll be covering the Euler-Bernoulli beam theory next. So I first cover the 1D elastic bar, and in the 1D Euler-Bernoulli beam theory, the beam can bend, and so we already derived this. I'll go really quickly over it, but what we found is that this is the only term that's necessary, and these other terms are boundary terms that become very clear when you look at Euler-Bernoulli beam theory carefully. And when you go through this derivation, which I already did in a previous lecture, you find that the total potential energy is just this one here at the bottom. And to extremize pi, all you have to take is the partial of pi respect to epsilon. Again, I use v. I've been using eta in the past. It's okay, it's the same thing. And when you do that, you can then minimize the total potential energy. You will then get when you do that, you'll go through all that step, which you've done a few times now. And when you integrate by parts, again, you get the Euler Lagrange equation, which is a strong form of the problem. And again, just to remind you, when you solve the Euler Lagrange equation for W, that W is the one that minimizes the total potential energy, which is actually incredible that we can derive this, because when you went to mechanics of materials, I'm pretty sure you didn't derive it this way. In fact, a number of assumptions were made. You were told these are the equations, but the derivations for those equations were not very clear. They just gave them to you for you to use. Now you know where it comes from, and not just that, you know that there's errors in this equation. It's not a perfect equation. And we also discussed the shortcomings in the Euler-Bernoulli beam theory. So very beautiful, very to me is just an insane idea that calculus of variations, when applied to pi, when I first find the first version of pi and set that equals 0, what I actually get is the function, an equation, a partial differential equation. Then when you solve for W, is the one that minimizes the functional. And just to remind you, pi is a single number. When you put so say I want to assume that W is a sine function or some function. When I plug it in here and I integrate over the domain, what I should get is a single number. Okay, so while pi depends on W, yes, it depends on W. But when you plug in a particular a function of W, what pi gives you is actually a number. Okay, just remember that. Don't forget it. And so the idea there then was to plug in an approximation function for W. Hey, I don't want to solve this. It's too much work. I don't want to have to deal with that. I don't want to integrate these 4 times, or I don't want to, plug in e to the x in here and try to solve for the differential equation. Instead, I'm going to approximate. I'm going to say, I apologize. I'm going to go in and put an approximation function here, and this phi naught will take care of any non-homogeneous essential boundary conditions, and the phi i's will take care of the essential boundary conditions, making sure that satisfy the homogeneous form of the essential boundary conditions. And then now the only unknowns are the ci's, and I'll plug that into here, into my potential energy. And when I do that, I get this beautiful equation here. And now notice how pi, when I plug in W for W tilde, that approximation function now, this pi now only becomes a function of C's. Now these phis depend on X. When I integrate that over these things that have x on them, that will give you a number. So the only unknown is c. You can see that there very clearly. It looks very crazy, the equations, but it's nothing to be worried about. Then what I showed you is I'll then um, take the derivative of pi respect to c1, the derivative of pi respect to c2, the derivative of pi respect to c3, the derivative of pi respect to cn. And then how many equations I have? I have n equations. How many unknowns I have? I have n unknowns. So guess what? Now I have a linear system of equations, which is amazing because I turned a problem whose solution, I mean, the solution to this is clearly a quadratic equation, some cubic equation. But if I had plus kw here and some other term here, the solution is actually a lot more complex. It's e to the x cosh function something. So it'll be a lot more complex solution. But guess what? I turned the problem into an approximate solution that is a linear system of equations. And so all you have to do is to approximate a solution using this algebraic system of equations. And when I find this C1, C2, C3, C to the Cn, and I plug them back in here into my approximate solution, guess what? This approximate uh, function that I came up with now the C's that I know now, they could be 2.1, 2.3. So the CIs are known, that approximation, which is the one that minimizes pi, is actually also the approximate solution to the strong form, which again is a very insane idea. It's actually, to me, this class is by far one of the best courses I've ever taken because I don't know, it's just insane. It's just a great idea. Okay. We talked about how the Rayleigh Ritz approximation method needs to follow the following guidelines. Each of the basis functions has to be continuous and differentiable. It needs to be sufficiently differentiable. For example, I cannot use a linear function here because if I use a linear function here, the second derivative of w will become zero, and you cannot have zero squared and then find the integral of that. That does not make sense. You will not be able to find the minimum. The approximate function has to be sufficiently differentiable. That means that the function has to be sufficiently smooth. The basis functions have to be complete and linearly independent. And the approximate function you select listen to me, has to satisfy the essential boundary condition. That's a very important idea that needs to be really considered. Okay, you have to keep that in mind. Here's a very quick example that I covered last week. We have in the last lecture, I apologize. Example one was a Rayleigh Ritz order Bernoulli beam. And you see here that if I have a clamp condition, I'll just plug in here W tilde into the total potential energy. This is not a, I'm sorry, this is not a clamp beam with a concentrated load at the very end, but it's a cantilever beam where it has a distributed load instead. So the left-hand side is fully fixed. So clearly W at zero has to be zero. You can see that happening. W prime at zero has to be zero, which you see that happening. So I plug in this W tilde in here, and now you can clearly see that pi becomes a function of just C1 and C2. You can now take the derivative of pi respect to C1 equal to zero, derivative of pi respect to C2 equal to zero, two equations, two unknowns. You can see here that I can do that in Mathematica very easily. So W is this much. I plug it into my functional, which now is a function when I do that. And when I plug it in here and integrate it, I get this equation here, which depends on C1 squared, C2, C1, and C2 squared. You can see that here. And now I can solve it using Mathematica. And clearly you can see I did it much easier here than what I did in the last lecture because you can write these things compact. But last week, the last lecture, I was showing you step by step how it's done. But in a very compact manner, the solve within Mathematica in one step will give you the C1 and C2. Very beautiful, very, to me, is great. I mean, it's just very nice. Um, okay, so this example I like because the slope is zero, but the deflection on the left hand side can occur. And let's say we put a deflection of W naught. Well, guess what? The phi naught will take care of that boundary condition. At x equals 0, you can see that quickly I get W at 0 is W naught, so that worked out. But if you take the first derivative of W, you'll find that W naught goes away, and then W prime at 0 is 0. You'll find that. So it works out. No slope, very nice. And the total potential energy is given here. And when you plug in W tilde here, again, very nice. You're able to solve for C1 and C2. And when you put that in Mathematica, very nicely, you get that the deflection of the tip, believe it or not, is PL cubed over 3I with an extra W naught. Because if I move this to, if I move this, then you'll expect the deflection to be affected. uh, this PL cubed over 3I is correct for W naught equals 0. You may have seen that from mechanics of materials. The next example is a functional that's given to you. This is a functional 1/2 u prime squared plus u squared plus 2u. And the idea is to find, let's figure out what the strong form of this is. So what is a function u that minimizes f? I did it here quickly, but I'm not going to spend time on that. When you solve it, uh, this is the governing equation you get. This is the Euler Lagrange equation you get. U double prime minus u equals 1, and these are the boundary conditions. If you solve for u in this equation, that'll be the one that minimizes the functional f or maximizes. You'll have to check the second variation. Pretty sure you're going to find that it minimizes it if you try doing it yourself, which I think you should because I think it's a good idea. So if I want to approximate the solution to this u double prime minus u equals 1, what I want to do first, I want to satisfy the boundary condition of u naught, u at 0 equals 1, because that's a non-homogeneous boundary condition. So you will find that you have to put a 1 here to make that happen, because u tilde at 0 has to be 1, because that's the boundary condition of the problem. And u prime at 1, that you don't have to satisfy. That's not an essential boundary condition, so you don't have to worry about that. So this is what you get, 1 plus c1x plus c2x squared. And what you find there is that when I plug this in into the functional f, when I plug it in here, and then I find this derivative of f respect to c1, derivative of f respect to c2, again, in Mathematica, very easy. You specify the approximate function, you integrate it, and then you can solve for C1 and C2. And the beautiful thing now is I can plot it. The analytical solution, you can see, looks very messy, but the approximate solution gives you just the same. I'll say that's the same. I mean, it's not the same, but you have to agree with me. That looks pretty close, very close. Um, okay. So we'll go now to the next example, which is a Rayleigh Ritz bar this is an interesting one. It's a modulus. Nowadays, with additive manufacturing, perhaps you can apply a functionally graded functional. I can't even say, but it's called FGM. Um, um, a functional graded material, and the modulus here is varying from the left to the right, according to this equation. There is a load applied that's like that, and clearly I'm clamping on the left hand side, so uh, you can enforce the essential boundary condition. The only essential boundary condition for an axial bar is u tilde at 0, 0, so enforce that, and so this c naught goes away. And a good approximation function for this then becomes u tilde x equals c1x plus c2x squared. And now that I have that with c naught equals 0, I'll plug in what E is. E is this formula here with the area that goes here. Maybe it's a constant cross section. And then take the derivative pi respect to C1, derivative pi respect to C2, and then you can find the coefficients C1 and C2 with two unknowns, two equations. I've done that here a little bit. You can minimize it respect to, take the derivative respect to C1, the derivative with respect to C2. And when you do that, that's the first equation. That's the second equation. And then you get a linear. The reason I wanted to plot it this way is to show you that what you get is a linear system of equations, a matrix of knowns, because you know the length of the bar. You know C1 and C2. You don't know C1 and C2. You know the right-hand side completely. You know E naught, you know Q naught, because these are knowns, are provided. So all you have to do is invert this matrix. So notice how we're able to find U tilde, so we can find the deflection of the bar as a function of length. You know, depending upon where you are in the bar, I can find how that deflection occurs, which is actually a pretty neat problem to look at. Um, yeah, very nice. And so now, and the reason I wanted to go through this example is to show you what you will do next if I want to find stresses. So if I know U tilde, then I know the strain, because strain is U prime. So du dx gives you the strain. So the strain is linear based on this approximation. And then the stress becomes modulus times strain, which becomes this equation here. So notice how the stress varies across a bar, which is something you probably didn't expect, but it's what's going on there. Okay, so that's what we have for this example. Very nice. I'm very excited about what's going on here. Just give me a minute. Give me a minute, please. So then I'm able to get the stress as a function of x. In the next example, um, example number 5, and perhaps this example you've been looking for is I have the left boundary condition fixed, the right hand boundary condition fixed. Again, I need to enforce the boundary condition. So when I enforce a C naught is 0, so select the quadratic equation if you have two essential boundary conditions to come up with the form of the approximation. U tilde at L has to be 0 because it's fixed on this end. Enforce that and come up with the form of the polynomial. So you get U tilde x is this, and you can check it. For example, U tilde at 0 is 0. Obviously, U tilde at L is also 0, because if I put L here, L divided by L is 1, 1 minus 1 is 0. So clearly that's 0. And so phi1 is 0 at the locations where essential boundary conditions are specified, which is exactly what it needs to be. And so then you can go ahead and plug in this approximation, U tilde. I just put one coefficient only. You can make many more coefficients if you want, but you can solve for C1 based on this. So in summary, the minimization of a functional with respect to a function implies the strong form of the problem. We found out that was the Euler Lagrange equation. We can substitute an approximation function into the functional, minimize a functional with respect, which is now is a function with respect to the unknown coefficient, and that indirectly approximates the solution to the strong form or the Euler Lagrange equation. The Rayleigh Ritz method, though, requires a functional, and if you don't have it, you can derive it based on the governing equation. So let's look at the more general formulation, a more general formulation of the problem. Again, I showed you this equation earlier. Here U naught is a strain energy density. And if U naught exists, then you definitely have a conservative deformation process. We talked about that already. If I have this, now all I have to do is to make sure that the U, uh, these UIs are kinematically admissible, meaning they satisfy the essential boundary conditions exactly. So among all kinematically admissible deflections, let UI denote the exact solution to the Euler Lagrange equation in volume V, and the natural boundary conditions on the portion external to the surface where TIs are prescribed. Displacement functions UI are the ones, these are the ones that render the first variation equal to 0, but not only that, is the one that solves the Euler Lagrange equations, which also means that it renders the system in equilibrium. Very exciting idea. But what we can do then is approximate the solution to this total potential energy. And the most general theory for 3D, not the most general one because it's only good for elastic materials, is to go ahead and approximate, use Ritz basis functions. I can select a function for U1, a function for U2, and a function for U3. This I here is a free index. It shows up everywhere. So UI here is one, for example, and then you want to have a summation of m through 1 through n. And so you can now solve for these coefficients AI once you plug it in here into the functional here. So that's the most general formulation. You'll get a 3n by 3n linear system of equations, which you can solve numerically. And these fees are selected in a priori to satisfy the essential boundary conditions in a way that's smart, to make UI kinematically admissible, to make it satisfy the essential boundary conditions of the problem. Then you can impose stationarity of the approximate total potential energy by setting the first variation of pi equal to 0, which means that you get these three n equations. For linear elastic material and or elastic material and dead weight loading, the total potential energy functional is quadratic in the deflections. For this quadratic functional, you will have three n equations, three n unknown Ritz coefficients, and you'll be able to then solve the problem. And how we choose this Ritz basis function, again, the fees need to be kinematically admissible, meaning they have to satisfy, the phi naught has to satisfy the inhomogeneous form of the boundary conditions. The phi I, the rest of them has to satisfy the homogeneous form of the essential boundary conditions. And S2 really here means the essential boundary conditions. And you also have to make sure that the fees that you select are linearly independent so that you have a solution that's complete. You also want to make sure that you have a complete set of polynomials or sine functions, whatever you use, because if they're not, then you won't be able to reach convergence. So completeness really is defined with respect to the integral over the domain and does not necessarily guarantee pointwise convergence of the dependent variables within the domain. So that does not necessarily mean that when you increase the number of constants or unknowns, that this will give you pointwise convergence. But what it really means that the energy will converge to a minimum value. Here's an example. I like this example because it resembles a beam, a wing problem for an aircraft. So you have your lift, which is approximated with this equation, and EI is a modulus. You can make EI also varying if you wanted to. And I don't want to go and dive into what the equations look like, but we already derived the Euler Bernoulli beam equations. They're given here at the bottom. I don't have to repeat the derivations again because we already derived it for you. I've been using W, but V is just fine. V is a transverse deflection. Why not? X, I've been using X1, but I use X here. Why not? That's okay. I'm forgiven for that. This is total potential energy for that problem. And again, now this is the equation you have. And if you apply for the specified loading that we have, this is your Euler-Lagrange equation that comes out of here when you render this functional stationary. So if I solve for V from this equation, plug it back in here, that's the one that minimizes pi. The boundary conditions are well known. We know it's clamped on the left-hand side. So that means the slope cannot change, is 0. And also the deflection at that end is 0. So therefore, V0, V at 0 is 0, V prime at 0 is 0. I only have to satisfy the essential boundary conditions. If you want to solve this equation exactly, you can do that. Integrate this 4 times, and this will be the solution to the problem if you were to find the exact solution. Um, Good luck with that. You know you can do it very quickly if you wanted to. And if you substitute equation 6, which is this exact solution, and you substitute that equation 6 into the potential energy, which you're allowed to do, by the way, you can substitute if you wanted to, uh, you'll find that pi becomes this number. I like showing that because it shows you that pi takes specific values for functions you select, which is totally fine. Just remember that. Pi is a numerical value for a given function w or v that you select. Um, so a lot of people forget that pi is actually a number. But if I were to select any other function, say select a function that's not the solution, I guarantee you, select any other function that's not the solution to this equation. If you plug it in here, guarantee that that pi will be greater than this value here. Because we know for a fact that the one that minimizes the functional is actually the exact solution. Anything else does not do that. So you'll get a pi that's different. It's not the one, okay? That's the minimum. So that to me is exciting to show. It's kind of exciting to show that. Now I can use a kinematically admissible lateral deflection that looks like this. I should start at from 2 to n because these terms are not kinematically admissible. Oh, and how will I know that? Is because if I included these two terms, I will not get del or v equals 0 here, and I will not get v prime equals 0 here. So I need those to be 0 there. So I know that it has to at least start quadratic, which I've done now several times. Oh, you're done. Substitute this equation into the functional here, and then minimize pi respect to each of those unknown coefficients, with derivative pi respect to am, and for uh, m equals 2, 3, up to whatever terms you want to select. And when you do that, for n equals 2, which means that I only have only one term, so from 2 to 2 basically, you can solve it. You can solve for a2, and then pi gives you this number. And I guarantee you that pi will be greater than the pi that you get from the exact solution, because obviously it's an approximate solution. An approximate solution will never be equal to the exact to the minimum of pi unless you get the exact solution. The moment that you can calculate is this, but I'll discuss this later. For n equals 3, you get a2 to be this, a3 to be that, the coefficients or unknown coefficients. And then pi for these unknown coefficients gives you this one. Now I guarantee you that pi decreases from here. For n equals 2, this pi is going to be greater than the pi with n equals 3. And as I increase the number of terms, the pi that you get is going to start approaching the exact value of pi for the lowest value you can ever get, which is the exact solution. I love this example. For n equals 4, I can solve for a2, a3, a4. And again, I can plot pi, find pi. And pi now gets even lower and is getting closer and closer to the exact solution. So what is the percentage error in the Ritz approximation compared to the exact solution? You can see here that the deflection at the very end. So if I want to look at a deflection at point L, at this point, that tip deflection, you can see how the error quickly vanished to 0. You can see that pi, if you compare the approximate value of pi to the exact solution, that the error also decreases quite fast to 0.14. That's a percentage error, so that's basically 0 if you think about it. And then you can also look at, you can see here how the moment at this end, here, which can be found. So the moment, remember, is EI V double prime, and I've been finding the approximate value of V. So if I plug it in here, you'll see that that moment can be calculated. So I did the moment calculation here for n equals 2. I did the moment calculation here for 2 terms, and then I did it for 3 terms, the moment calculation. So I can compare against the exact solution. And when I do that, you can see that the error is kind of lingering pretty high there. Not too bad there, but still pretty high. I mean, not too bad. Um, Now when I look at shear, you can look at the natural boundary conditions. I'll also look at what the moment looks like, moment and shear for n equals 2, n equals 3, n equals 4, the actual value. And what you see here is a lateral deflection, which is this one. The lateral deflection for n equals 2 is here. but for n equals 3 looks really nice. Look at how that n equals 3 solution gets really close to the exact solution. But when I look at the bending moment diagram, though, the bending moment, the exact solution is this one here. But look at n equals 3 doesn't look that good. You can see that there. And n equals 4 looks much better, right? Much better. But n equals 3, not that good. N equals 2 is a straight line, right? And if you plot the shear, things go really, really bad.